Hello once again, students. I wanted to finish up talking about exercise 16. This is the one where we're defining brand new orderings of sets. So, and again, we're starting quite simply here with whole numbers, and we want to create a set of rules such that we can mechanically define 2 as being the lowest element of the set. I know 2 is not lower than 0, but that's kind of the point here, is I can make it such that it will be the lowest element. So we'll start off, we can make this arrangement that you see here, this infinite set of whole numbers, so long as we exclude 2 from sets of possible elements here, where y is not 2, that is, then 2ty will be a true statement. Again, where t is effectively defining this order, okay? And I will define the second part down here where I'll say xty, just like where x is less than y as a whole number set. So long as, of course, I'm not dealing with 2 being either x or y. Then we move on to b. Now we got the same kind of thing going on, but now I'm ordering 0 and 2 below the rest of the numbers. So again, I do in a similar fashion. I'm going to exclude 0 and 2 from my statements. I'll say 2ty, and again, from my x and y statements, I want to be able to say xty will be where x is less than the y. Again, so long as I'm saying x being 0 or 2 is excluded from the set. I'll have a valid ordering here. The second thing I have you do here, okay, so that exercise 16 was on that one example. Consider this example as you move on to exercise 17. Consider this arrangement here of whole numbers. So now I've got a first term and a last term, but yet it's still an infinite set. So this is going to be a very, very peculiar linear ordering here. The way this is defined, of course, I'm saying where x and y, other than 0, I can say x relates to y, just like a less than relationship of whole numbers. And again, where x is not 0, I would say x relates to 0. And the relationship now is r sub 2, and that's just an arbitrary name. We could have called it Fred, doesn't matter. Part A, of course, says that all our whole numbers are going to be ordered just like you would have otherwise. And part B is just saying and everything is less than 0. So this makes things a little strange, because now I've got both a first and a last element. But even weirder is that when I have whole numbers, ordinarily with whole numbers, you could say numbers have, neighbors. That is to say, 5 has 2 immediate neighbors, 4 and 6. On our new ordering here, of course, 1 just has 1 immediate neighbor. Since 1 was now our first element and 0 is our last, 1 just has 1 neighbor, 2. But 0 has nothing next to it. See, on a regular whole number ordering, everything's got neighbors, including 0 has 1 neighbor, just the 1, but not on this new one here, not on our new relationship. Or now I've got this 0 with no immediate neighbors. There's always going to be something I can wedge for any whole number x. There's always going to be a new whole number I could wedge in between x and 0 if it's defined like this. You see? So on exercise 17, you're going to create a new linear arrangement based on these rules. So this time they've given you the rules where our new linear order t will be 0tx for any non-zero x's, and x and y will be such that, again, as long as I'm not dealing with 0, that xty will be x is greater than y. Your task on exercise 17 is to enter into these blanks. I'm even spotting you. I'm telling you where to put ellipsis. The ... saying, hey, there's a bunch of things in between here. There's 7 boxes for you to fill in that there's an exact ordering that will be defined by these 2 simple rules on this problem. Now, again, as you complete exercise 17, note it's very closely related to the example above, and I've even thrown the points of ellipsis in to help you out. So for today, I want you to complete exercise 18 on page 13, and I will see you again soon. Please subscribe to my YouTube channel and smash that like button, and have a great rest of your day. Bye now.